Welcome to Study Loop.
Hello friends, here it is given a vapor compression refrigerator cycle. Vapor compression refrigeration cycle is used to keep a space at low temperature. Find mass flow rate of R134a fluid, coefficient of performance, exergy destruction in each component. Second law efficiency and exergy destruction of the cycle. Let us see here the analysis. For analysis, we have to use the properties of R134a liquid fluid using table A11E and A13E. P1 20 psia, fluid quality is 1, that is saturated vapor. Entropy is 102 point. Sorry, enthalpy is, I am extremely sorry, it is enthalpy or thermal capacity, VATU per pound mass, and entropy to be 0.2257 VATU per pound mass. So all these proper values we are taking from the table. So no such calculation is required. P2 140 psi, temperature T2 is 160 degree Fahrenheit, thermal capacity is 131.37 VATU per pound mass, and entropy to be 0.2444 VATU pound per mass. Pressure of third state 140 psia. Quality of fluid is 0, that is this is saturated liquid. Thermal capacity of the fluid is 45.31 VATU per pound mass, and entropy to be 0.09 215 VA2 per pound mass per rumor. H4 to be equal to H3 45.31 V at U per pound mass. Pressure P4 20 psia. H4 45.31 V at U per pound mass and entropy to be 0.1001 VATU per pound mass per rumor. The energy interaction each component and mass flow rate. Work input H2 minus H1 131.37 minus 102.74, that is 28.63 BATU per pound mass. Heat transfer at high temperature H2 minus H3 131.37 minus 45.31, so it is to be 86.06 BATU per pound mass. Heat absorbed at low temperature, heat transferred at high temperature minus work input 86.06 minus 28.63, so it is to be 57.43 BATU per pound mass. Mass flow rate of fluid, rate of flow of energy at low temperature to amount of the heat flowing at low temperature. This value is given in problem. So from problem you have to take it. It is to be 45,000 upon 3600 BATU per second, or heat absorbed from the low temperature is given 57.43. So it is to be 0.2177 pound mass per second. Now, the coefficient of performance is defined as heat absorbed at low temperature to work input 57.43 upon 28.63, so it is 2.006. The exergy destruction is defined as entropy generation for compression. First we are finding for compression. Entropy generation from process 1 to 2, S2 minus S1, 0.244 minus 0.2257, that is 0.01874 V at U per pound mass per rumor. Exergy destruction, rate of exergy destruction in process 1 to 2, mass flow rate into ambient temperature into entropy generation In process 1 to 2, so 0.2177 into 540 Reaumur, 0.01874. So exergy of this is exergy of compressor. Now exergy of condenser. Entropy generation in the process 2 to 3, that is S3 minus S2 plus heat transfer at high temperature upon temperature of high hot junction. So it is to be 0.09215 minus 0.2444 plus 86.06 upon 540. So it is to be 0.007073 BATU per pound mass per Reaumur. So exergy destruction of condenser, mass flow rate, ambient temperature into entropy generation in the process 2 to 3, 0.2177 mass flow rate, temperature 540 Reaumur, and entropy generation is 0.007073. So it is to be 0.831 VATU per second. So this is the exergy destruction of condenser. Now for expansion valve, entropy generation in the process 3 to 4. So S4 minus S3, 0.1001 minus 0.09215, that is 0.007961 BATU per pound mass per Reaumur. So exergy destruction of expansion ball will be mass flow rate, ambient temperature into entropy generation 3 to 4. Substitute the value 0.2177, 0.007961, temperature 540. So it is to be 0.9358 BATU per pound mass. In case of evaporator, entropy generation for the process 4 to 1, so S1 minus S4 minus heat absorbed at low temperature upon temperature of low junction, cold junction you may call. So it is to be 0.2257 minus 0.1001 minus 57.43 upon 470 number. So you will get 0.003. So entropy generation for the process 421, we will get 0.003400 VATU per pound mass per Reaumur scale. So exergy, destruction of evaporator, mass flow rate, ambient temperature into entropy generation from process 421, 0.2177, 540, 0.0034. So on solving it, 0.3996 VATU per pound mass. For second law efficiency, first we have to find power input. The power input is defined as 1 minus exergy rate of destruction in process 122, power input 2.203 upon 6.232, that is, sorry, I have done it wrongly. I am solving it again. Just, I am extremely sorry. The power input, first we will find power input. Power input is mass flow rate into work input 0.2177 into 28.63, that is 6.232 BATU per second. Now second law efficiency is defined as 1 minus exergy rate of destruction from 1 to 2 upon power input, so 1.2.203 upon 6.232. So it is to be 0.6465 or 64.7%. The total energy destruction of cycle work done input minus exergy at low temperature, that is 6.232 minus 1.862, so it is to be 4.370 BATU per second. We can also obtain by adding the exergy of each component. That's all. Thanks for